Okay, so to see why these two random variables are close when n is big and p is small, let's can start with the x, the PMF of x. So the probability x equals k, right? Probability x equals k is equal to this. We're assuming k is a reasonable number, like 0, 1, 2, 3, something like that, up to n, something non-zero. Okay, so now we have to tear apart this expression here. And let's also make a substitution with lambda in here. So we have, this is equal to, if I write this out like this, n factorial over n minus k factorial. And here I have p to the k. Let's, instead of p, let's write lambda over n to the k. And let's write 1 minus lambda over n to the k. To the n minus k. Okay, so let's see. I have k of these. And yes, okay. So we want to see if we can get this to look like the Poisson. I see already I have lambda to the k and k factorial here. So let me take this outside. So I have n factorial over n minus k factorial. So also I can, well, let's just do it in a couple steps. So I have n minus k factorial, and I have 1 over n to the k. So what's left? And here I have, I'll keep this for one more step, I guess. 1 minus lambda over n to the n minus k. And over here, I have what I wanted to get out, lambda to the k over k factorial. Okay, so this is looking like the PMF for the Poisson, if this is looking like e to the minus lambda. Do you see it is already? Can you already see that? Maybe not quite yet. Let's write this out now. There's really only two or three more terms, 2 or 3 more things to consider. So first of all, I'm going to write this as k terms in the numerator. So this is n minus 1, n minus k plus 1 in the numerator here. And in the denominator here, I have n to the k. So I'm just going to write this like n times n. So they all have an n to go with there. All right, for the other thing here, I'm going to write this as 2 and this is still here. I want it to keep this. Okay, well, now, as n gets big, since k is fixed here, n gets big, this should go to 1, right? Because if n gets big and k is not too big, which is reasonable, I want to know the probability that k is some number like 0, even up to whatever, up to 50, even up to big, any finite k, but it's easier to see it if k is not too big. Then these fractions here all get close to 1. So this goes to 1. So this term approaches 1 as n goes to infinity. So if n is reasonably big, that term goes to 1 and things are looking good. Also, this up here also, we have 1 minus lambda over n to the k. If n is big, and k is moderate, and p is what is this, k? Yeah. Remember, lambda over n is p, really, basically. So if p is pretty small, I have 1 minus p, and I'm powering it, but k is not too big. This should stay near 1, right? So as n gets big, if lambda is held fixed, this goes to 1 as n goes to big. But the point was, even for finite things that don't go to infinity, you see it's going to be pretty close to 1. Now, also, 1 minus lambda over n to the n, this goes to e to the minus lambda. And this is just a limit. This is from calculus. Use L'Hopital's rule. We'll do it for you. Okay, so you can show that goes to e to the minus lambda. So there you have it. So for big N, and lambda equal to NP, the probability y equals k is approximately equal to the probability x equals k. And that's our argument there. We saw above in the example above, it worked pretty well. Okay, thanks.